Okay, hello everyone, welcome to our next lecture. This is the next lecture of the course on Cyber Physical System Fundamentals. In this course I'm teaching Embedded Systems Foundations of Cyber Physical Systems. This is the 15th lecture, and this lecture is corresponding to some of the material covered in chapter 5 of the Great Companion textbook. So that is the chapter entitled Evaluation and Validation. So just to remind you, we are considering a number of activities that have to be performed during the design iterations. And these activities include evaluation and validation of the different partial designs. And you should remember from the last two lectures that there are different criteria by which we can evaluate these different designs. And you see from the large set of symbols on this slide that there are indeed many different criteria. Today I would like to start off by continuing the discussion of average and worst case delays. That means I'm looking at performance information, performance evaluation of our designs. And I will start this course by first of all covering some material which is really standard and which is really something that people must know that who work in this area. This is a so-called real-time calculus or modular performance analysis. The name really depends a little bit on whether we look at a low level of detail or whether we consider the impact on the system level. With these techniques, we are addressing the fact that in embedded and cyber physical systems, we do in many cases process streams of events. So we have to consider certain streams of events that are coming either from a network or from some sensor. There are special cases of such streams of events that are kind of standard cases that are usually considered whenever we do some analysis, whenever we are looking for some example. One such case is the so-called periodic event stream, where we have events that happen periodically, so this is actually time. So after a certain amount of time, we expect the next event. And as a certain variation of that periodic event stream, we have periodic event streams with jitter. That means we still stick to the idea of having some period, but now for each of the periods we can have a certain jitter. That means the events can happen up to j time units earlier, or they can happen up to j time units later, but we assume that the period in any case will remain fixed. So these event streams is what we consider therefore real-time calculus. Real-time calculus was proposed by Lothar Thiele and his co-workers from ETH Zurich. It is based on network calculus. It is actually an adaptation of network calculus to real-time systems. In this real-time calculus, we have to consider first of all upper bounds and lower bounds on the number of events that can arrive within a certain time interval delta, because these upper bounds and lower bounds will give us some information on the required processing performance. So therefore we are considering these upper bounds and lower bounds of the number of events that arrive within a certain time interval delta. First of all, let's try to do this for the periodic event stream. And for the periodic event stream, we can, in order to derive the upper bound on the number of events, consider a situation in which we start the observation just a very small amount of time before the next event occurs. And it doesn't really matter how small that amount of time is. Actually, very soon after we start our observation, we will observe the next event. That means regardless of how close we get over here to delta equals 0, we will observe one event. and and when we make this window larger, we will still have observed that one event. Now if we make that window even larger, and if we make it larger than p, we will have observed the next event, because the next event will occur exactly p units of time later. That means after, if we increase the time window delta to beyond p, we will have observed the next event, and if we make it even larger, we will have observed the next event. So that means we will have observed a total of 3 events. Now this is what we call the upper bound in terms of the number of events. We can also try to derive the lower bound, that's the minimum number of events that we could observe. And we obtain the lower bound if we assume that we start our observation just a very small amount of time after the last event has happened. It doesn't really matter how small that amount of time is. We will always not immediately observe one event, so that means we will start with a value of 0 there, and we will not observe any event until our delta exceeds a value of p. If we exceed a value of p, then we will have observed one event, because at that time there must have been one event. And the same argument also applies if this delta becomes larger, then we must have observed 2 events. Now, if you have followed this discussion very carefully, you might have observed that I did not really tell you a lot about the values that we would observe for delta equals p and delta equals 2p. Now, in fact, the discussion of the amount of events that we would be observing for these values requires some very subtle limit value considerations, so I'm leaving them aside, and I'm not telling you something about the values at exactly those lengths of this time window delta. Now, similar arguments can also be discussed for the case where we have a periodic event stream with some jitter. There again, in order to consider the maximum number of events that we can have in some time window delta, we assume that we are starting just immediately before the next event happens. So therefore, we will be starting with one event, no matter how close we are starting next to delta equals 0. But now, since we have this jitter, the second event might occur j time units earlier, so the second event might occur j time units earlier, and the third event will also happen j time units earlier. So please note that we assume that the jitter doesn't accumulate. The maximum deviation is by j time units, and we never talk about the deviation by 2 or 3 j time units. Now, if we look at the lower bound, we have to understand that, of course, initially for delta pretty close to 0, we still have as a minimum no event, but then it can take up to j time units more until we have observed the first event, but then it's guaranteed that we have observed one event, and this continues on until it's guaranteed that we have had at least 2 events. So this is the description that we need in order to know how many events we have to take into account. And that's obviously very important if we would like to know whether or not our performance, the performance of the underlying execution platform, is sufficient. Now, there's a second pair of functions that we need in order to characterize our system, and the second pair of function is describing the service that's available from our system. Towards this end, we have so-called service curves. These service curves describe the upper bound and the lower bound on the performance on the number of executed instructions, for example, that's available from our system. And again, we are considering these time windows delta, if we had a case, say for example, where for some processor we have a constant number of instructions that can be executed, we could characterize that processor by such a straight line where this would be delta again, and in the other direction we would be having the number of executed instructions. Now, to consider a somewhat more complicated case, I'm looking at the situation where we have a TDMA bus, and again for this TDMA bus we are trying to find an upper bound and a lower bound on the information, on the amount of information that's communicated along this TDMA bus. In order to derive the upper bound, we are considering the situation where our observation starts exactly at the time when the bus is allocated to the communication partner that we are currently considering. And that means from that time onwards we will linearly be increasing the amount of information that is transmitted. So therefore we have this straight line over here. And this continues on until this time window is closed, until the bus is allocated to somebody else. And from then onwards we have no additional information communicated for the partner that we are currently considering. And this is the case until finally this period P has elapsed, and until this bus is again allocated to the partner that we are considering. So in this way we have these periodic increases of the amount of information that's communicated. In a similar way, we can consider the case where we would like to derive a lower bound on the amount of information that is transmitted. For this purpose, we assume that our time window starts exactly at the time when the bus is deallocated for the partner that we are considering. And that means that for some time no information is communicated, and this is guaranteed to be the case until P minus S time units have elapsed, but then we are pretty sure that communication must take place, and from then onwards we have a linear increase in the amount of information that is communicated, and then the bus is deallocated again, and we have no increase in the communicated information. So using these service curves, we can characterize the service that can be provided by our system. There is a third ingredient that we need in order to study the performance relations for a real-time system, and that is the so-called workload characterization. The workload characterization again consists of two functions that describe upper and lower bounds. In this case, they describe the amount of work that is required as a maximum or as a minimum per incoming event. That means that in this particular case shown in the slide, we assume that the worst case execution time per event is in this case 4, and that the best case execution time in this case is 3. So therefore, obviously, if we have 2 events, the worst case execution time in total would be 8, and the best case would in this case be 6. Please note that the straight lines have been added there for visualization purposes only. Actually, this function gamma is only defined for integer values of the number of events, because we don't have any fractional values there for the number of events. Now, what I described so far is consisting of a pair of functions that either provide a mapping from the domain of time intervals delta to a number of events or to certain times. So in the case of the alpha functions that I described so far, we have a mapping from these time intervals delta to a certain number of events. And in general, whenever we have a function that is providing a mapping to a certain number of events, we will use these bars there on top of the function name. So alpha upper bound bar describes a certain number of events. Now next we would like to characterize how much execution time is actually required for the incoming event stream, and we know that these functions gamma, in particular the upper bound for the function gamma, is describing the maximum amount of workload that is generated per event. So therefore also using that mapping in addition to this alpha bar mapping, we compute the upper bound on the workload for any time window delta. So that means alpha without the bar describes the actual workload where the mapping now is to real time units. The same can be applied for the lower bound. In order to derive the lower workload that is required, we can use the lower bound for the number of events that are arriving, and then use the minimum execution time that we need per event, and as a result we are computing the minimum workload in terms of real-time units that is required for the incoming event stream. From this we can also compute upper and lower bounds for the service capacity which is required. So for example, we can assume that there is a certain service capacity available. This service capacity now is computed in terms of time units. We can provide this inverse mapping of these gamma functions, and as a result obtain a certain service capacity in terms of events. And we can do the same thing here for the lower bound. We start with the service capacity, then take into account the upper bound on the required execution time, and as a result get a lower bound for the service capacity in terms of the number of events. That's why we are using the bar there. Now, with this information, we can compute the behavior of a complex system. A complex system in which we are using so-called real-time components. And for these real-time components, we have incoming event streams, and we have incoming streams of available service. And as a result, we are obtaining new event streams. These are outgoing event streams, and there are remaining service capacities. Now, I could claim that on this slide, in order to make sure that you really follow this presentation, I have added these floor operators there so that you'll really start wondering why I added the floor operators there. However, this is not a floor operator, this is just a problem with the graphics on my computer. All these floor operators should actually be squares. So that's not my fault, there was no way to really display correctly the brackets there. Okay, so we are talking about events that are characterized by their lower bounds and their upper bounds, and we are talking about the service capacity that is arriving and the remaining service capacity. The idea is that we might have a kind of pipeline processing for events. Events are coming in, there is a certain operation applied onto this event stream, there is a new event stream produced by this real-time component, and this new event stream is then forwarded to the next real-time component, and there is some remaining service capacity. Obviously we somehow assume that the event stream down here is processed with a lower priority, because this event stream up here will get all the service capacity and the event stream down here will obtain only the service capacity that is remaining. Now the question is, how can we compute the outgoing event streams and the remaining service capacities? Now fortunately, real-time calculus does give us a closed equation for the resulting event streams and for the remaining service capacities. So we see over here that for the resulting arrival curves we have a closed form for the upper bound and the lower bound. It looks pretty complex. It does involve both the upper bounds and the lower bounds of the arrival curves. It does include the available service capacities, and in this way we can characterize the resulting event streams. Also, we can characterize the remaining service curves. The precise computations don't really matter. The authors of the corresponding papers are providing MATLAB toolboxes that incorporate all these functions that you see here in the diagram. So the functions look rather complicated. However, it is very easy to really compute the resulting service curves and the resulting arrival curves. Details of the proofs can be found in the relevant references, so I refrain from actually demonstrating the proof that will demonstrate how we arrive at these equations. Interestingly, the results also include bounds on the buffer sizes and on the maximum latency. This is very important because in this way we know by how many cycles we are delaying at a maximum these events. The theory has found many different applications. It has been extended into many different directions. So for example, it has been shown that the theory can also be used to compute the remaining battery capacities, something that is very relevant for battery-driven systems. Now I'd like to briefly demonstrate how the theory can be applied to an example which I have already used in chapter 2. It's the same example in which we are using an in-car navigation system where we have this user interface and where we possibly have traffic messages. You might remember that there the idea was that we have 3 different use cases and that for the different use cases we have specified delays. So for example, there was this use case where we want to change the volume, and for this we have a certain specified delay. You also might remember that we had these other use cases, and you could remember possibly also that we described the use case using sequence charts, and that we had annotated sequence charts where in the sequence chart we explicitly specified how many events we are going to have, and in the same way we were specifying how much information we were communicating per exchange of information there. Also, we can assume that we have information on the execution time that's required per use case, so that means that we are assuming that the worst case and the best case execution time are actually known, and we assume for the sake of simplicity for this example that they are the same, which in general they are of course not. So, and we know that there is a maximum time delay which is specified. In a similar way, we can demonstrate this second use case where we want to look up some destination address, and again we assume that there is a maximum delay which is specified. And we know that this use case can be modeled by using sequence charts, and we know that for this sequence chart we can also annotate the chart with the corresponding time and volume information. The same applies to the use case of incoming TMC messages. There again we can specify the delay, and again we can describe this use case by using a sequence chart. Now for this application development, we can consider different proposed architectures. So for example, we can use one architecture where we have one processor there for the navigation system, one processor for the man-machine interface, and one processor for the radio, and we can consider the case where these 3 processors are connected by a rather low-speed bus. Then we have a second architecture with 3 processors again, where the processors are only connected to the man-machine interface, again using a low-speed bus. And we have a third architecture where 2 of the kind of virtual processes are merged into one. So both applications work on one processor, and that processor has a higher performance. And we have a fourth architecture where the merging is done between two different parts of the application. And finally, we have an architecture where we use a more powerful processor, and all the three all the three components, all the three parts of the application have been merged into one processor. So then we can try to model that application. First of all, we look, for example, at the address lookup. We have assumed already in chapter 2 that there is at most one address lookup per second, and this means that we can characterize the arrival curves of this use case. We know that there is at most one incoming event per second, and we are just looking at the case where we are actually using the system. So we also assume that there is a minimum of one event per second. In order to simplify the mathematical treatment, we can safely approximate these upper bounds and the lower bounds by straight lines, because that makes the mathematical treatment a little easier, even though the considered bounds will be somewhat less tight. Then we can also consider the resource model. In this case, we use a very much simplified resource model where we assume that we have a single RISC CPU which executes instructions at a constant rate. And since the rate is constant, the upper bound and the lower bound are the same in this case, and this line really depends on the processing power. The angle for this line really depends on the processing power of that processor that we're using. We can then furthermore assume a rather simple mapping of the different applications to the different processes. We are assuming, and this will be motivated later in the next chapter, we are assuming that we give the highest priority to that use case which can happen with the highest frequency, and that means changing the volume. We give the next lower priority to that use case that has the intermediate period, that means a period of 1 second, and we allocate the lowest priority to that use case that has the largest period. We will motivate in the following chapter that this is actually a special case of so-called rate monotonic scheduling, where this allocation of priorities makes some sense. In this way, we can set up the performance model. We can see in this case that changing the volume has actually received the highest priority. We can see that we are passing the incoming stream of events through that processor. It's transmitted over the bus, and using the flow of information, we know that we have to send the incoming events to the processor processing the application, the part of the application corresponding to the radio, and the result is then fed back to this man-machine interface, and this is actually the end of processing that particular stream of events. And we can also consider the propagation of events for the use case of address lookup. There again we can refer to the sequence chart, and we would see that we need to communicate this stream of events there to CPU 2 that is implementing the navigation system, and the resulting stream needs to be sent back to the man-machine interface, and that's the end of processing for that stream. And finally, we have this last use case that needs to be processed by the radio system, by the navigation system, and also by the man-machine interface. Now with this model we can do the analysis, so you don't see really a change there on the slide. It's only to indicate that now we assume that the analysis is actually performed. And we can, as a result, figure out what the resulting end-to-end delays would be. I told you that the real-time calculus will allow us to compute the resulting end-to-end delays, and this is what we are interested in. This slide shows you the end-to-end delays for the different use cases, and you can see that for the first two architectures we have rather large end-to-end delays. You see that for 3 out of 4 use cases we have pretty large delays there, and if we would like to go for smaller delays we would need to use any of the last 3 architectures there. The first 2 are really too slow, and that's why they are included in these red boxes. We can try to figure out why this architecture A is so poorly performing. We can try to figure out where in this architecture we actually have a bottleneck. For this purpose we can incrementally change the parameters of our architecture. For example, we can incrementally change the relative speed of the processor that we're using for the man-machine interface, and we can see that with the initial speed we have a very large delay for the incoming TMC messages. However, if we replace that processor by a somewhat faster processor, we can reduce that delay significantly, so architecture A could be used as well if we would modify the speed of the processor which is used here. So this is an application of real-time calculus. I think it's easy to understand that modeling such applications is not very complex. These models can be designed in a rather short amount of time. For these cases, it has been mentioned that about half a day was needed. The evaluation of a particular architecture is pretty fast. So according to the source information, the evaluation takes about 1 second per evaluation. So that means that we can really analyze the design space that's available. Also, we can see that very little information is needed to design these models, so it is appropriate for being used very early during the design phase. And I think it was obvious that the equations that are involved are actually very complex. However, this complexity is kept away from the engineers because everything is integrated in a toolbox, and the engineers don't need to understand all the mathematical operators. They just need to understand their application, and they need to understand some basic parameters about their architecture. So that concludes the description of the modular performance analysis.